Hey everybody, Matt here, and I am back at the live coding. This week I'm going to implement a really simple routine to compute the vector dot product in Python. Now, the dot product is a base operation in matrix multiplication. It's got some cool geometric properties, but the goal here today is not to develop an ultra high performance implementation, but rather demonstrate the use of a technique called test-driven development to take the requirements of the dot product algorithm, convert those requirements to test cases, and then use those test cases to guide the code that we're writing for this implementation. First thing, we need to actually set up our imports. Our testing framework that we're going to use here today is called PyTest. It's very powerful. We're just going to use the very basic surface functionality. We're going to bring in NumPy for our benchmarking. Then we're going to need to bring in the function we're testing. So from the dot product module, we're going to implement a function that we're going to name dot product. So those are our imports. Now we're going to write our tests. And writing tests is pretty easy with PyTest. You effectively just define a series of functions with test assigned as a prefix to the function name. So our first test is going to be for those vector lengths. So we're going to have test unequal length fall into the body of this thing, and we're going to make two spoofed or fake vectors that we're going to use to do our testing. They're just going to be simple. We'll make an a vector x with 4 elements in it, and then we'll make a vector y with 2 elements in it. Okay. Now we want our code to either execute normally if vectors are equal length, or I want it to raise some sort of error if we have ragged vectors. So we're going to use the context manager to take with PyTest to access the raises method, and we're going to ensure or test that an assertion error is raised when we have two vectors of unequal length passed to dot product. Okay, so there's test 1 for unequal lengths. Now we need to test for our scalar output. If I could type. Okay, so there's our scalar output function name. Let's copy and paste these two vectors and maybe modify them just a little bit. Let's make them equal length. Okay. We're going to take another variable called output. We're going to use type, take dot product, and then pass it vectors x and y. So what is this one-liner doing here? We're taking our two vectors x and y, passing it to dot product, computing the result, returning it, taking that return result, and figuring out what the type of that result is. Then we're taking that type and assigning it to variable output. Now we're going to come down here and use an assert statement. So we're going to get inside the assert statement, take our output, and check if it's equal to either an int or a float. So we have some Boolean comparisons and some conditional comparisons. So if either one of these are true, we will return true for this portion of the statement, and that true will be fed into the assert, which will also return a true, allowing us to pass our test. So that's our scalar output test. Now finally, let's do our benchmarking with a test called result. Let's grab these two vectors. It's good practice when you're writing tests to have each test function test for one specific thing. But it's okay if we're reusing these vectors in one way or another. Let's go ahead moving forward, just a small aside. So now we have numpy x is equal to numpy array x. What we're doing here is taking our list vectors and we're converting them to numpy vector arrays. We'll do the same for y. Pass it y. Okay, so we have our list vectors and we have our numpy vectors set up. And now we're going to assert that dot product xy. So the result returned from dot product xy is going to be equal to the result returned from numpy x dot numpy So we're asserting that whatever is returned from these two test vectors are equal. So zoom up here. So here's our tests that we're going to use to guide our development. So we have a way to test for ragged vectors, we have a way to test our scalar output, and we have a test written for our actual result to make sure whatever we're computing has an equivalent computation in NumPy's implementation. So we're going to jump over to our actual dot product module, and we're finally going to start writing some code. Okay, so thinking about this plain English here, let's go ahead and write a function called dot product. We need two vectors, vector 1, vector 2, passed as keyword arguments. Okay. The first test that I'm going to tackle is actually I'm going to focus on the result. I'm going to focus on the result first. Okay. So thinking about this plain English up here, I need to know how many elements to iterate through. So I'm going to take a variable called m, and I'm going to assign it to the length of vector 1. And then we also need a place to accumulate our total sums of all the products of the element pairs. So I'm going to take another variable called alpha, and I'm just going to assign it to 0. Now, for each element pair, so for I in range of m, so this is the length of our element pairs, so that's our iteration length. We're just simply going to take alpha. We're going to set it equal to vector 1 at index I, so we're going to pull out the element at index position I in vector 1, and we're going to multiply it by the element in vector 2 at the same index position, and then we're going to add it to alpha. Okay, and then finally we are going to return alpha. And the long and short of it, in the guts of this function here, that's really all the code we need to compute our dot product. So let's see if it actually gives us reasonable results. So we have our tests written over here, but now we need a way to run them. So we're going to hop over to our terminal. Ooh, a little foreshadowing there, but we're going to clear all that out. I'm in my terminal here. I'm going to type in pytest, and I'm going to pass it the verbose flag so we can see everything, all the tracebacks, all the failure and passing information. And we're going to run this thing. We can see down here in the footer, we had one test failed and 2 tests passed. So that's a good sign. If we roll up to the header, we can see that our result was correct, so we passed there, and our scalar output was correct, and we passed there. So we still need to deal with our vectors of unequal length. All right. So as you can see, when you're doing this TDD, you write a series of tests, you write a little bit of code, you run your tests to see what passes or fails, and then you reassess your development. It allows you to kind of divide and conquer. So we know our scalar output and our results are good to go. So now we can focus on figuring out how to get this unequal length test to pass. So let's go ahead and minimize the terminal, and let's focus on that final test. So we're back in the body of this function, and I know that I want the code to check the vector lengths early in its execution, and I want it to do something if the vectors are of equal length, and I want it to do something else if the vectors are not of equal length. So we're going to use an assertion statement to simply check the length of vector 1 against the length of vector 2. Okay, and then we want to provide a message to the user of some sort if this assertion fails, so a false is returned. We'll just say vector lengths are not equal. Okay, and what is going to go on under the hood if this assertion fails? So if we have either of these vectors are of unequal length, it'll return a false. And at this point in the code on line 13 here, an assertion error will be raised. The code will stop executing, and it will let the user and the program know that something's wrong and allow them to take countermeasures. But if the vectors are of equal length, the assertion will pass with a true, and execution of the code will continue into the body of the function here, where we'll actually compute the dot product and return a result. So let's test it and see if it works the way we think it is. Let's come down here, clear this all out, run PyTest verbose again, and bam, much shorter this time because we have all of our tests are greened up. Okay, so this is a good sign. Let's rearrange this just a little bit and perhaps review. So we just use test-driven development to take 3 requirements for the dot product algorithm, write them into test cases, and then use those test cases to guide our development. Now, I feel like we could argue that we've come to a point that we have a reasonable implementation of this dot product function. It may not be the fastest, it may not be the best, but at least it's returning the results that we need, and it's following all the rules of the algorithm for the most part. Moving forward, now we could take this function and start working it into a larger application or project. Perhaps we could use it as a base operation for computing vector matrix and matrix-matrix multiplication. And if you were doing that, you could also bring these tests with it and integrate it into a larger test framework. So every time you change code anywhere in your application or your project, you simply rerun your tests, ensure you're all greened up, and you can identify places that you're introducing errors or bugs with the changes you're making. So that's really the long and short of it. Thanks. See you later.